What is X-ray? So X-ray is nothing but it is basically electromagnetic radiation, right? It is a kind of EM. EM means electromagnetic radiation or wave, you can say. But what is interesting thing? Interesting thing is its wavelength is very small. If you see that wavelength is denoted by lambda, for X-ray that wavelength is lie in the range of 0.001 to 10 nanometer. You can think, now we can understand how much small it is. So the wavelength of X-ray is very small, of the order of the size of unit cell, you can say. The wavelength of X-ray is very small. It is a kind of electromagnetic wave, or you can say it is a part of electromagnetic wave having very short wavelength. In other words, you can say if the wavelength is small, definitely the energy will be very high, right? Because you know that relation for EM wave, the energy is related to lambda, and that is hc by lambda. For X-ray, that lambda is very small. That's why energy will be very high. So we can say that X-ray, that wavelength is small. It means its energy is high. Okay. So what are the applications of the X-ray? Anyone? So the applications first, to determine that crystal structure. To determine the crystal structure. To determine the crystal structure. In condensed matter physics, you will learn this like simple cubic structure, BCC structure, FCC structure, etc. This structure you can understand from that X-ray. To understand that crystal structure like simple cubic, BCC, FCC, HCP, okay, triclinic, monoclinic, that structure you can understand by using X-ray, or basically you have to use X-ray diffraction. Okay, next, to differentiate between amorphous and crystalline structure. In addition, please write that third applications. It has biomedical applications also. So first application, to determine that crystal structure like simple cubic in bracket, BCC, FCC, this is all are the crystal structure. So that crystal structure can be understood by using X-ray, and that setup is nothing but X-ray diffraction. You people know, right? Also, to differentiate between that crystalline and amorphous crystal structure, that can be understood from X-ray. Further, the X-ray can be used for biomedical application. Okay, So this is all about that properties of X-ray and its applications. Properties means it is a kind of electromagnetic wave, or you can say it is a part of electromagnetic wave having very small wavelength. In other words, it will have large energy values. Since E is inversely proportional to lambda and lambda is small, so you can say that energy of this X-ray will be high. Okay. Now, how will produce this X-ray? Okay. So how will produce? Anyone in the class? Shekhar, how will produce X-ray? Because it is important to produce that X-ray because it has very varieties of applications like crystal structure, then differentiate between crystalline amorphous structure, biomedical application. In addition, it has application in ranging also to find out that range. That will come in later. Since it has large number of applications or varieties of applications, so you have to produce this X-ray. So how will produce this X-ray? Anyone? So I'll discuss this production of X-ray. So you will have on vacuum tube, okay, this side you will have filament, okay. So this is your vacuum tube. On the right hand side you will have filament. On the left hand side you will have target, okay. So this is the kind of spherical, this is vacuum tube. This is your vacuum tube. This is your vacuum tube. This is your filament. This is your filament. Okay. This is your target. And that target basically use that material for target basically use heavy metal having high melting point. Example, in most of the cases, tungsten is used as a target material. So you have that setup for production of X-ray. You have vacuum tube. Vacuum means there is no air. So for vacuum purpose, you have to use rotary pump, turbomolecular pump. So there is no air inside this tube. On the right hand side, you have filament, and that filament is connected with cathode. Cathode means negatively charged, and the target is connected with anode. Anode means positively charged. So there is a bias between that filament and target. So target is positively charged and filament is negatively charged. Inside tube there is no air. So why there is no air, I'll come to that picture. Also the target material should be heavy metal and it should have very high melting point. Now see what is the interesting thing is happening. When you are heating that filament at very high temperature, if you heat this filament at very high temperature, there will be emission of electron. There will be stream of electron that will be produced here. So if you heat this filament, there will be stream of electron that will be produced. Now, interesting thing is that this side is negatively charged. So of course that electron will get repulsed. And this side is positively charged. So obviously that electron will be attracted. So that now due to this biasness, the direction of motion of electron is fixed, that is towards target, and electron is accelerated since this potential is very high, of the order of 5 kilo electron volt, 10 kilo electron volt. You can think how much big it is. Since this potential difference is very large, so electron will get accelerated at very high kinetic energy. So what I means, it will accelerate towards the target at very high kinetic energy. So at the end, when it will strike this target, at this time it will have very large kinetic energy. And why there is vacuum inside the tube? Because if there is some particle here, that will collide with electron and electron will lose its energy. Okay, electron will lose its energy, so it will not able to reach here. That's why the main motivation is to create this electron, and it should reach that target material at very high kinetic energy. So that's why you have to keep this tube free or empty, you can say. How will create this vacuum? You have to use two pumps, that is rotary and turbomolecular pump. So by using these two pumps, you can create this vacuum, so there will be no air inside this tube, so electron will easily flow through this path, or there will be no obstacle. So electron, while it is bombarding this target, at this time it will have very high kinetic energy. Now why this target material is having a high heavy metal? Heavy metal means what? Heavy metal means it will have large Z value. Z value means large number of atomic number. And why it has high melting point? If it has low melting point, then it will be melted. When that electron will stuck, it will melt. So your purpose of creation of or production of X-ray will be failed. That's why the target material should be heavy metal. Why it is heavy metal, I'll come, but it should also have very high melting point, so that when that electron having very high kinetic energy, it is bombarding, that time it should not be melted. Did you people get what I'm saying, or shall I repeat? Now I'll come how that X-ray will produce. Did you people get what I'm saying, or shall I repeat?
Yes, great.
Every people got till now? So there is one question,
Yes, sir.
why that heavy metal we should use for the production of X-ray. But before that, we have to understand how the X-ray is creating. Okay, so I'll erase this. Shall I erase? Shall I erase this?
Sir.
Okay.
Yes.
Now let us assume, or let us draw one atomic structure of target material. Target material basically use most of the time tungsten. Okay, so let us draw that atomic structure of target material. So inside you have plus ZD charge, and I said for target Z is very large. So what will happen? You have electron also that is revolving around this path. Sorry, my diagram is not good. Okay, but I am giving that structure. So this is the on atomic structure. I have taken on atom of target material. So this is your basically K cell, L cell, M cell. So you will have electron here, and you will have many electron on L cell also, right? In L cell also, and similarly in M cell also there will be many electrons. Now what will happen? You see, the electron from filament is coming at very high kinetic energy. So this is your incident electron that is coming from filament having very high kinetic energy. So what will happen? If it has very high kinetic energy, so it can able to enter inside that atom. It can able to enter inside that atom. You can think how much energy it has. It has very large energy, very high kinetic energy. So it can reach to the atomic inside that atom of target material, and then what it will do? It will interact or collide with inner shell electron. So suppose this electron, incident electron, is colliding with K shell electron of target material, then what will happen? Its kinetic energy will be absorbed by this atom, sorry, this electron. So that incident electron having very high kinetic energy, that will strike that inner shell electron of target material, and inner shell electron will absorb this energy, kinetic energy, and it will be ejected from that atom. Did you get what I'm saying? So incident electron from filament having very high kinetic energy, so it can easily reach to the atom of the target material, and what it will do, it will interact with inner shell electron of target material, and it will give its kinetic energy to this fellow, and because of this, that electron will be ejected. Now there will be void space, right? So you will have void space here in inner shell. So now from upper shell, so from upper shell, that electron will make transition from here to here. So when that electron will be ejected, there will be void space. To fill this space, electron from higher state will make transition. Okay. So when there is a transition, definitely there will be emission of photon. And for heavy metal, that energy of the photon means the energy difference between these two states, right? Energy difference between these two states. So when electron is making transition from higher to lower state, it will emit photon, and for heavy metal, that photon is nothing but X-ray. So your heavy electron from filament having very high kinetic energy is giving that kinetic energy to inner shell electron. Inner shell electron will absorb this energy, and it will be ejected back. So there will be free space or void space at the inner shell. To fill this space from higher state, electron will make transition, and because of this transition, there will be emission of photon. And I'm saying for heavy metal, that photon will be nothing but X-ray. So this kind of X-ray, this kind of production of X-ray is known as characteristic X-ray. So there are two kinds of X-ray that will be produced. So due to this kind of phenomena, there will be production of X-ray, and that is known as characteristic X-ray. Any doubt? Shekhar, Karthik, any doubt, Tej? Please respond me.
No,
so
sir.
Are you enjoying class?
Yes, sir.
Okay. Every people enjoying class? So there are two kinds of X-ray. So if that X-ray is produced due to that electronic transition, then this is known as characteristic X-ray. Also, characteristic X-ray is discrete in nature. I mean that whatever X-ray will get, that will have some discrete energy. That will have some discrete energy. So characteristic X-ray is discrete in nature. Please note that. So this kind of X-ray is characteristic X-ray. Now we'll come to continuous X-ray. Shall I erase? Shall I erase?
Yes, sir.
Okay. So there are two kinds of X-ray based on the production. There will be two kinds of X-ray. One is characteristic X-ray that I discussed. Another kind of X-ray is continuous X-ray. Okay. So what is basically happening in continuous X-ray? So again, I am drawing. So this is your target atom having plus Jd charge inside nucleus, and electron is orbiting. And I said that plus Z number is high. Heavy metal means Z number is large. So now suppose I said that electron that is coming from filament having very high kinetic energy. So it can enter to the atomic orbital of target material. Now we see electron is negatively charged. So when it is coming close to the nucleus, so there will be Coulomb attraction because electron is negatively charged and that Z is very large. So you know that Coulomb force is nothing but Q1, Q2. So Q1 is electronic charge, Q2 means that plus Z charge. Definitely there will be attraction, force of attraction. Definitely there will be force of attraction between these two. So what will happen when that electron coming close to that nucleus? There will be force of attraction, so electron will deviate from its path and it will come like that. And also electron was accelerating. When it deviates from its path, it will be retarded, or you can say it will continuously lose its energy. When electron is accelerated towards this direction due to Coulomb attraction, when that Coulomb attraction will be high, when that separation is small, because you know that also F is inversely proportional to R square. When R is small and you already have large amount of Z, so because of this there will be high attraction, so electron will be deviated from its original path and it will continuously lose its kinetic energy. So due to that conservation of energy, you can say that loss of kinetic energy is converted to or converted by production of X-ray. So continuous X-ray is basically producing by retardation of electron, incoming electron, or you can say by continuous losing of kinetic energy of incoming electron due to high amount of Coulomb attraction when it is very close to the nucleus. And continuous X-ray means you will have many number of wavelengths of this X-ray. So if you draw that continuous X-ray, suppose along y-axis you have intensity of X-ray and along x-axis you have applied potential or V. Oh, sorry, you have lambda. So along y-axis you have intensity of X-ray and along x-axis you have lambda. So we'll get many number of wavelengths having non-zero intensity. It means in continuous X-ray you will have many number of wavelength of X-ray. But in discrete X-ray you will have only one or two line. Okay, is it clear to all? There are two kind of X-ray. One will be created due to that electronic transition from higher to lower orbit, and another is there is a continuous loss of kinetic energy of incoming electron, and due to this there will be creation of X-ray, and that is known as continuous X-ray. Continuous X-ray will have many number of wavelengths. So if you draw that intensity versus wavelength for continuous X-ray, will have this kind of picture. So you will have many number of wavelengths. Is it clear to all? Is it clear to all? Okay. Also, based on the energy of X-ray, there are two kind of X-ray. Two types, and that is basically based on energy. One is a hard X-ray, hard X-ray means this hard X-ray will have very high energy. Very high energy, and that energy, if you do not buy capitally, it should be lie in the range of 5 to 10 kilo electron volt. So it means it will have low wavelength. Another is soft X-ray. Soft X-ray means it will have low energy, right? It will have low energy or large wavelength. Okay. Is it clear to all? Now I said that that target material should have large Z, right? Target material should have large Z. But you should ask me why it is large. That atomic number of target material is large. Why it is large? That should be a question, right? That should be a question. Why it is large? I'll give that answer. Shall I erase? Shall I erase? Okay. You know, for hydrogen-like atom, the energy of nth state will be how much? That is nothing but 13.6 into Z square by N square. Okay. So when that electron is making transition from L to K, in K, N is how much? For K orbital, N will be how much? On, right? For K orbital, N will be on. For L, it will be N will be 2, right? And that due to this transition, you are getting that X-ray I told. That is, you are getting X-ray. Okay. Now, how much will be the energy of this X-ray? So for this K, N is 1. For L, N is 2, right? Is not it? Every people, are you getting what I'm saying? Are you getting? Shekhar, are you getting?
Yes, sir.
Yes, yes. So because of for K orbital, you have N will be on. For L, N will be 2. And due to that electronic transition from L to K, you are getting that X-ray. That energy of that X-ray is nothing but energy difference between these two states, right? So how much will be that energy? Delta E will be energy of this state, that is minus 13.6 Z square by 2 square. It means Z square by 2 square means 4 minus, or minus you have already have a minus minus plus, you will have 13.6 Z square by on, because for final state. So what I have done, energy of that outgoing photon or X-ray will be the energy of this state initial minus energy of final. So initial means N equals to 2. So Z square by N square will be 4. Minus of minus means plus 13.6 into Z square by 1 square means 1. So if you calculate it, you'll basically get 13.6 by into 13.6 into how much? 3 by 4 Z square in EV. Is it okay? Calculation is okay, Shekhar? Is it okay? 13.6 into 3 by 4 into Z square EV, right? So you see that energy of photon is depends on Z number, right? And I already told you for X-ray energy is very high. So for production of that photon, having very high energy, you should have large jet. Is it clear to all? Is it clear to all? Okay. Shall I erase? Okay. Every people enjoying class?
Yes, sir.
Okay. Now,
All part board use, sir.
sorry?
Left side we use board.
Sure. Are you enjoying class? Are you enjoying class?
Sir.
Okay, good. Now we'll discuss about that Mosley law. Any people know? Mosley's law. Any people knows? So we'll discuss about that Mosley's laws. It basically describes that characteristic of X-ray. It basically describes the characteristic of X-ray. So you know, when the electron is coming from Ni state, where Ni is the principal quantum number, when it is coming to NF state, that wavelength we have already derived, right? 1 by lambda equals to R Z square into 1 by Ni square minus 1 by NF square, right? Every people remember that? Every people remember that?
Sir, it's 1 by NF square minus 1 by NI square.
Yes. Thank you. It should be 1 by NF square minus 1 by Ni square when electron is coming from higher to lower state. And that was basically for Lyman series, Balmer series, Parsons series, Humphreys series, okay, bracket series. But for X-ray, that is basically modified by Mosley. And what he said, for X-ray having wavelength lambda, the 1 by lambda should be equals to R Z square, not Z square. He has taken on constant, that is known as, anyone? So what he said, for X-ray 1 by lambda equals to R into Z minus sigma whole square into 1 by NF square minus 1 by Ni square. So basically for Lyman, Balmer, Parsons, that belongs to UV, visible and IR. That formula was simply 1 by lambda equals to R. R is Rydberg constant into Z square. Z is the atomic number of hydrogen like atom. Then you have 1 by NF square minus 1 by Ni square. But for X-ray, that wavelength or 1 by lambda equals to, there will be modification in Z. And here that sigma is known as screening constant. Screening constant. Okay. Now if you multiply C both sides, then what you will get on the left hand side, anyone? If you multiply C both sides, then you will get on the left hand side C bar lambda is nothing but what?
2.
Huh?
2.
New, right? Very good. Also 1 by lambda, I told what is that thing. 1 by lambda is known as wave number, right? So if you multiply both sides by C, C is nothing but speed of light. So C by lambda on the left hand side will provide you the frequency of X-ray, and that should be equals to how much? You have R, then you have C, then Z minus sigma whole square, then you have 1 by NF square minus 1 by Ni square. So frequency of X-ray is nothing but R times C into Z minus sigma whole square into 1 by Nf square minus 1 by Ni square. Okay? Did you people get? Okay. Now if you assume or if you take square root, so square root of frequency equals to square root of Rc into 1 by Nf square minus 1 by Ni square inside bracket, then you have another factor that is Z minus sigma. Okay. So finally what you have got, I'll write here that square root of frequency of X-ray will be nothing but some constant A into Z minus sigma. Sigma is known as screening constant and it depends on line. For example, I'll write it. So what is the conclusion or what is Moseley's law? The square root of frequency of X-ray is directly proportional to that atomic number of target material. Square root of frequency of X-ray is directly proportional to the atomic number of target material. Is it clear to all? Where A is what? If people ask me what is A, so A you can easily write. A is nothing but here R times C into 1 by Nf square minus 1 by Ni square. Okay, that is some constant. Is it clear to all?
Yes, sir.
Okay. So after that he has draw on diagram that is based on this formula. So if you take square root of frequency along y-axis of X-ray and atomic number that is along x-axis, so you will basically get this kind of straight line. So square root of frequency is directly proportional to the atomic number of X-ray. Okay, is it clear to all? Is it clear? Any doubt in the class? Now that screening constant, most of the time in your question you will get screening constant is on. I said that screening constant is dependent on line. So for K line or for K series, shall I write? So for in question you will get for K series, and for all other series, for L series it will be some different. I'll tell you. For K series, what is the meaning of K series? What is the meaning? K series means basically Lyman series, right? Electron is coming to n equals to 1 from all higher state, right? Is not it? Is it clear?
Yes, sir.
Yes. So K series means electron is coming at final state, that is n equals to 1, or basically it is coming to ground state. For K series, sigma is 1. So then it will be modified. That formula will be square root of frequency will be how much? Will be simply equals to A into Z minus 1. For L series, that sigma value will be approximately 6.5. Okay. But in your question you will get for K series only. Okay. Is it clear to all? Is it clear to all? Okay. Are you enjoying class? Any doubt? It's a really interesting story, right?
Sir,
Yes.
how did we get sigma equal to 1 for K series? Can you repeat?
How we'll get this? Actually, this is an experimental thing. Okay. For you will get this by looking at transition. You know, suppose electron is coming from n equals to 2 to n equals to 1, and it is emitting some energy, right? Suppose electron is coming from n equals to 2 to n equals to 1. So it will emit some energy, and that energy will have some corresponding, frequency. For K series, I am giving example. So electron is coming from n equals to 2 to n equals to 1. It will emit some photon. Photon will have some frequency. So for this transition, you will get some frequency, and A value will get from this equation. Final state, initial state, and all other things you know. If it is coming from this to this state, you will get another photon having different frequency. So two frequency we got. Now if you use this formula, suppose one is gamma 1, another is gamma 2, and A will be some different. Suppose this is A1. Why A will be different? Anyone? Why A will be different? Because the final state is different, right? A is nothing but root over RC 1 by NF square minus 1 by NI square. So since A is different, so let us assume for first transition, that is from n equals to 2 to n equals to 1, let us take this constant as A1. Okay, and you know that which target you are using. That is, you know, for tungsten that Z is fixed, for other Z is fixed. So you know that Z will not change for any target, but for gamma 2, A will be changed. Let us assume that is A2, and that is Z minus sigma. Now if you calculate gamma or difference, if you calculate this difference, gamma 1 square root of gamma 1 minus gamma 2, all other quantity you know, only what you know, you don't know sigma, right? All other quantity you know. A1 you know from this equation, A2 you know, Z is known because you are using the target, you know that Z values. Only you don't know screening constant. By calculating this difference, you can easily calculate that sigma value for K series. Is it clear to you?
Yes, sir.
Very good. Are you enjoying class, every people? Is it okay for all? It's a really interesting topic, right? Is it clear to all? Okay. Now we'll do few important problem. Okay, it's really interesting. Can you write this problem? Can you please write this problem? Okay. Sorry. So I'll do mixed problem, some X-ray problem, on some based on previous class. Okay. So sorry. First problem is calculate the de Broglie wavelength of electron. Calculate the de Broglie wavelength of electron in the third Bohr orbit of hydrogen atom. Calculate the de Broglie wavelength of electron in the third Bohr orbit of hydrogen atom. Calculate the de Broglie wavelength of electron in the third Bohr orbit of hydrogen atom. How will do this? Anyone? How will do? Anyone? So you know this formula, right? So that heading will be changed now. Some problem we are doing. So for third, you know this formula, right? Radius of nth orbit is nothing but, for hydrogen atom it will be n square a naught, and a naught you know that is 0.53 angstrom, right? Now for third orbit, n is how much? N is how much for third orbit? How much? Anyone? Please reply me. Anyone? For third Bohr orbit, n should be 3, right? Then radius will be how much? 9 a naught. Okay. So 9, you know that a naught is how much? 0.53 angstrom. If you write it in meter, it will be 5.3 into 10 to the power minus 11 meter. Okay. If you calculate it, R0 you will get 47.7 into 10 to the power minus 11 meter. Are you getting this? Please check. So you got this radius of third Bohr orbit. And if you remember, in first class, we have discussed the de Broglie wavelength, that relation from wave theory. 2 pi Rn should be equals to n lambda. Is it clear? 2 pi Rn equals to n lambda. So for n equals to 3, what you will write? 2 pi R3 equals to 3 lambda, where lambda is de Broglie wavelength. So from this equation, you can clearly say that lambda or de Broglie wavelength will be nothing but 2 pi R3 divided by 3. Okay. So it will be basically 2 pi by 3 into 2 pi by 3 into how much? 47.7 into 10 to the power minus 11 meter. Is it clear to all? Is it clear to all? Sekhar? Okay. Can you calculate
Yes.
this? Can you calculate this number?
Sir, 9.98 into 10 raised to minus 10.
Very good. So if you get, if you calculate it, you will definitely get 9.9 into 10 to the power minus 10 in meter. Okay. 9.99 also. Is it clear? So this number is nothing but 9.99. Okay. Is it clear to all? You will get this wavelength of third Bohr orbit, that is 9.99 into 10 to the power minus 10 meter. Is it clear to all?
Yes, sir.
Okay. Are you getting this number? Okay. We'll do one problem from X-ray. Another thing I forgot to share you. Please write this. In X-ray part, you write this continuous X-ray part. So we got this continuous X-ray, right? So minimum wavelength. If you remember, I'm extremely sorry that I forgot to tell you. If you see that intensity versus wavelength, you will have this kind of graph. So you have some minimum wavelength, right? Minimum wavelength at which you can see that intensity, some intensities are there. Below that, you will not get any intensity. So this all belongs to X-ray, but it will have some minimum wavelength. Okay, that minimum wavelength will be denoted by lambda mean, and that will be nothing but Hc by EV. So in continuous X-ray, you will get this kind of plot. So it all belongs to X-ray, but it will have some minimum wavelength. Below that minimum wavelength, you will not get any X-ray. It means below that intensity will be 0, and that minimum wavelength will be nothing but Hc by EV. H is Planck constant, C is the speed of light, E is the electronic charge, and V is what? V was that applied potential. If you remember, this side you have applied some positive number, and this side you have applied negative. So it means it is basically connected with some potential. So that potential is V, and that is basically V here. So minimum wavelength is basically in X-ray production depends on applied potential. I'm extremely sorry, I forgot to tell that time. Okay. Is it clear to all? Is it clear, Anju?
Yes, sir.
Okay. Now we'll do one problem. Okay. Please write this problem.
Sir.
Sorry.
And 10 to power 9 answer come.
How much?
Power minus 9 meter.
Minus
10 to power 9 meter. Got it.
10 to the power 9 minus 9 meter. Are you saying 10 to the power minus 9 meter? You are saying like this, right?
Sir.
Yeah, you see, 9.99 is almost 10, right? 9.99 means it is 10. Is not it? So if it is
Difference 10 to power 10, not 10 to power 9.
10 to the power minus 9 you are getting.
Sir.
Is it? How? This number 2 pi by 3 is how much? Can you check it? Anyone? Can you check? 2 pi by 3 is how much? 2 pi by 3 is how much? Calculate it. Anyone please reply me. 2 pi by 3 is how much? Basically it will be 2 pi by 3 will be how much? Almost close to 2. Because pi is nothing but 3.14, right? So 3.14 divided by 3 almost is unity. So basically this is multiplied by 47.7. So if you multiply 47.7 by 2, you will get how much?
99.02.
99.02 you are getting. 99.0.
99.02.
This number you are saying, right?
19 come. 999.02.
How? You are multiplying 2 by 47.7. This is not 477. This is 47.7.
Sorry, sir.
This is 47.7. No, I have calculated already here 47.7.
No sin, sir.
Okay. You can calculate it. It is very simple. You are multiplying 9 by 5.3. So obviously this number will come. 9 into 0.53 is how 5.3 is how much? 47.7, right? So 47.7, that dimension will not change. That will be, or order will not change. That will be 10 to the power minus 11. Now if you multiply, yes, now it's clear, right?
No look, so sorry.
Okay, no problem, no problem. Now please do one more problem, and that is part of X-ray. Okay, I hope you people enjoy that X-ray, right? And it will really be helpful in future. Okay, please write this, then I will stop. Or shall I stop? Because already going to 7. Shall I stop here?
Sir.
Okay, then tomorrow we'll do few problem, then we'll go to that next part. Okay, is it clear to all? Okay, then I'm leaving here. Okay. Okay, bye all.